Hello. All right, are you ready for some more DTFT? No? What? It's fun. DTFT is cool. And at this point, there's obvious differences between CTFT and DTFT, but, there are also a lot of similarities. So you should be happy that we're doing more of this. So one property that is useful and that has similarities to properties of CTFT is conjugation property, which says that if I know a signal x has DTFT x e to the j omega, then x star of n will have DTFT. You do two things. First, you star this, right? But that's not enough. You also flip the sign of omega. So it becomes x star e to the negative j omega. Right? Easy to show. I'm not going to do it. Because we've done something very similar in continuous time. It's almost identical. Okay? So that's the conjugation property. And the conjugate symmetry property is a result of a signal x being actually real. So conjugate symmetry means if it's a direct result, this is not a new result. This is just a corollary to this, right? If x of n is real valued, I'll say x is real valued because that means for all n is real valued. Then x star, of course, is the same as x, right? And therefore, x of e to the j omega has to be the same as x star of e to the negative j omega. All right? So if you look at the Fourier transform, if you compare positive omega to negative omega, you'll see this kind of symmetry. Okay? The left-hand side is the complex conjugate of the right-hand side. If it's real, even better. They are the same. Right? Okay? Now remember, this is something that CTFT doesn't have, that DTFT has. It is periodic with period 2 pi. Correct? So therefore, I can say a little more than this, or I can state this equivalently. I can note from periodicity that this is the same as x star. If I advance omega by 2 pi, I'm going to get the same thing. So this is the same as x of j 2 pi minus omega. Okay? So therefore, we have this additional property that is unique to DTFT because DTFT is periodic with 2 pi. All that this says is that since we usually look at the Fourier transform DTFT from 0 to 2 pi, and there's no special reason for it. You can look at it from negative pi to pi. It's periodic. You can look at it over any interval of 2 pi. But so far, we've done it from 0 to 2 pi. So that's why I wrote it in this form. So in that case, you get things like what we saw in our examples last time. So things that are symmetric, things like this, right? So the examples we discussed last time were all, I think, even symmetric. So they gave us real valued Fourier transform, except for one, I think the exponential one-sided one. And therefore, x was real. So when x is real, x equals x star basically means they are equal. So it shows you the symmetry property. Okay? So that means you have mirror image symmetry with respect to pi. And that's exactly what we observed last time. Okay? And even if your x is complex valued, of course, this holds for the magnitude, which is real valued and positive. All right. So, and one property I think I wrote down last time. If I did not, it's in the notes. It was the time reversal property, which said that x of negative n goes with x of e to the negative j omega. That's kind of easier to remember. You flip the sign of n, and that ends up flipping the sign of omega in the frequency domain, okay? If I didn't write this in class, it is in the notes, okay? So if I combine it with what I just discussed, we can then conclude that if x is even symmetric, meaning that x of negative n is x of n, then we can just use the properties we discussed. So this goes with x of e to the negative j omega. This goes with x of e to the j omega, and they must be the same. And in addition, from the properties that we discussed, we know that x of e to the negative j omega is equal to x star of e to the j omega, right? That is what we showed here. Wait, x, where is it? What am I doing? X. I completely lost track of what I'm doing. So x of e to the negative j omega, according to what we have, is x star of e to the j omega, right? So that's right. So that means we can actually relate. Wait, what's going on? We can actually relate these two guys, and that means, of course, for what I wrote here, we also need it to be real. Okay, if x is even symmetric and real, and this helped us at this point. Okay, so then I can claim x, the Fourier transform is x star, which simply means that we have a real valued one. Okay, so that's cool, and that's why some of the examples we looked at last time were actually real valued, because the signals were symmetric, even symmetric. So you can similarly argue that if x is odd symmetric, meaning x of n, negative n is equal to x of negative x of n, for all n, of course, not just for any n, for all n, then by similar arguments, you'll find that x is equal to the Fourier transform x, big X, is equal to negative x star. That makes it purely imaginary, right? Then x is purely imaginary. All right, so we kind of already used this property without quite proving it, because we had similar properties in continuous time. So already last time I said it's even symmetric, therefore it is real. Okay, so we kind of used this already. Any questions? Well, so okay, let's go back here. So here's what we claimed, right? So this is the same as saying that if I star both sides, it says x star of e to the j omega, right, is equal to x of e to the j omega, and that's what I wrote there. Does that make sense? So it's the same thing. It's the same idea, just rewritten. Okay. So the signal is not purely imaginary. The Fourier transform is purely imaginary. The signal is real, in fact. So, again, this needs to be written. If x odd symmetric and real, because of odd symmetry, Fourier transform becomes purely imaginary. So, last time I think we looked at the Fourier transforms for Fourier series, which ended up giving us impulses in the frequency domain. So, when you look at a sine function, it gave us a j at the frequency of sine and the negative j at the negative frequency of sine. So that is purely imaginary because it's j times something, right? And that's because sine is odd symmetric. Whereas cosine is even symmetric, and its Fourier transform had two impulses, nothing complex. Right? Okay, so now I'd like to derive something that's analogous to the scaling property in continuous time. So recall scaling property in continuous time. If I take my x and scale it by a, so the signal becomes x of at, that simply, if I'm compressing my signal in time, it's stretching it in frequency. If I'm stretching my signal in time, it's compressing my frequency, so I get that. But there is a factor that I need to add, 1 over a, absolute value in case I somehow took a negative value a. Okay, so we discussed this last time. So the question is, what would be something analogous to this in discrete time Fourier transforms, right? Well, the first question that arises then is, what is analogous to stretching or compressing a discrete time signal? Okay. First, the easy one. Is there anything analogous to compressing? Well, no, you're not sampling anything. I just gave you a sequence. Okay, we're not sampling anything yet. Okay, it's just a discrete time sequence, right? But it's a sequence. It's integer values, right? No. So how can I take, if I give you a signal like this, this is time equal to 1, time equal to 2, maybe something like this, negative 1. I can't possibly compress this. Where am I going to move this guy at 1? Right? I can't move it to 1/2. That's not defined. In continuous time, if you're compressing by 2, of course, that ends up at being 1/2, right? But here, there are only integer values. So really, we don't have anything like compressing the signal, but we can imagine stretching it, right? So what would be, if I want to stretch this by a factor of 2 in time, what would this stretch signal look like? Or what would a stretch signal look like? Okay, so for 0, nothing changes, right? But for n equal to 1, this guy should now appear at n equal to 2, right? So I skip 1, I put it at n equal to 2, whatever it was, all right? And this guy, let's mark it with a blue, that will now appear at n equal to 4. Okay? So then what happens at n equal to 1, n equal to 3? We created gaps. Okay? Well, you can put zeros there. That's one way of defining a, not the only way, but one way of defining a stretched version of the signal. Okay? So we'll use this idea to define a stretched signal xm of n, where m indicates that we've stretched it by a factor of m, okay, capital M. So the proper way to define this would be just to mimic what we did in this example with m equal to 2, right? This example used m equal to 2, a stretching factor of 2. The way to define this would be to say the stretch signal is equal to x of n by m when n is an integer multiple of m. Of m, right? Does that make sense? So in this example, when n is equal to 2, we're looking at x of 1, right? When n is equal to 4, we're looking at n equal to 2, right? So that's the rule. And for all numbers that are not integer multiples of m, like n equal to 1 in this example and n equal to 3 in this example, you just plant a 0. 0 otherwise, okay? So you guys agree the general expression that I wrote is consistent with our example where the stretching factor m is equal to 2? Yes? No complaints? Okay. So then the question is, what is the Fourier transform of this? If after this stretching, when I stretch like this, what happens to the dTFT? The answer is the so-called time expansion property. So this is the definition, of course. Time expansion property says that the Fourier transform of this guy, the stretched version, xm of n, is going to be very simple actually. We stretch, so what should happen in the frequency domain? The opposite, compress, right? And remember, in dTFT, there's sort of a mismatch between the time and frequency domains. Time domain is discrete, frequency domain is continuous, right? So when I mean stretch, I really stretch, right? It's just a continuous variable omega. So I just do e to the j omega m, which will really stretch it by a factor of m, right? Make sense? Okay? Easiest thing to show, it really is. So because what we are doing here is we are looking at the Fourier transform of the expanded signal. And that goes over n. And the expanded signal is this, xm of n, e to the negative j omega n. This is just the definition of dTFT, right? But note that what I have here is 0 when n not an integer multiple of m, right? So, even though we have the sum, a lot of the entries of this sum will be 0. So we might as well count over the non-zero entries. And we can do that by counting over a new index k negative infinity to infinity, at k times m, right? So I'm just going to substitute x for little n. I'm going to put k times m, because when little n is not k times m for some k, integer k, it is 0. So I'm not losing anything by writing it in this form, okay? And then again, little n is replaced by k m, all right? So, and I know that, at these integer multiples of m, by definition, xm of n is the same as this. Okay? So that is the same as, nope, not this. This is the same as x of what? Tell me. This is just a wake-up call. It's an easy question, but just, k, yes. And gets multiplied by this. So it looks just like, the Fourier transform definition applied to x of k, right? Except that, that definition would have just omega, whereas here I have omega times m. So that, of course, creates this term, x of e to the j omega m. So that's the proof. It's very simple. Okay. All right. So let me show you a figure. If you have no questions about this, let me show you an example from the notes. The notes are here. Okay, and yeah, wait, this is, what is going on? Oh, okay, so this was just an illustration of what I just did. Never mind that, that's not what I wanted to show you. Okay, here's what it is. So I give you a pair signal, which is a pulse, and it's dTFT, which is sort of a periodic sync, right? It's not exactly sync, because sync doesn't have symmetry with period 2 pi. But last time we saw some cousin of sync, which is sine by sine, and it also has the periodicity, so it's this one, right? So what happens if I stretch this signal by a factor of 2? M is equal to 2, right? Now the signal looks like this. So what happened is that I took this dTFT, compressed it by a factor of 2, and that's the dTFT, just like we learned, right? That's the property. And if I happen to expand the signal by a factor of 3 instead, then the DTFT gets compressed by a factor of 3. Okay? And you can actually make some interesting observations. So this is, if you look at the spectrum of the pulse at the very top, right? It does have, I used to have a pointer. I don't know if it's still alive. I haven't touched it in years. Still working. Good. So people watching the screencast, I guess, won't see this, but you will, which is not a big deal. Those who are watching, I'm just pointing to the top figure with a red pointer. Okay, you're not missing much. Okay, so we have this pulse. This is the DTFT. You sort of expect the types of things you want to see in the DTFT. A lot of the spectrum is concentrated around 0, which is the low frequency, right? But you do see a little bit of a spike at pi. That means the signal has a bit of a high frequency content too. What is the culprit for that if I look at the pulse? What do you think is causing that bump at pi? This jump, right? Anything that's too jumpy will lead to high frequency. So that's what you're seeing here. But now look, when I stretched it by a factor of 2, I made it much more jumpier, right? Much jumpier. Like at every other instant, you have to go back and visit 0. You do expect this to create an even more pronounced high frequency content, right? And indeed, we see this here in x of e to the j2 omega, because whatever was at 2 pi now got moved to pi. Right? So we have a much bigger high frequency spike. It was this much before, now it's a lot bigger. As expected, because we have to revisit 0 frequently. When I stretch by a factor of 3, I still have to visit 0, but at least once I'm there, I take another time instant to stay there, right? So it's not as bad, the jumpiness. And so you can then see that the spectrum, again, has a lower spike at pi. Okay? But it does have a higher spike here, which is the frequency. So this one here. Can you read that frequency? What do you think it is? So let's see. From 0 to pi, I have how many spikes? 1, 2, 3. Right? So at every pi over 3, I have a spike. Right? So now the big one is happening at 2 pi over 3. And that's not that is because we have this, periodic thing here, at least for a while, with period 3, right? So that's why it's aggravating that frequency. Whereas here, the periodicity in this interval was 2. That's why pi over 2 was being aggravated. Okay, so it's fun and very informative. Take your time to look at examples like this. It's more important than manipulating these summations and cranking out formulas, okay? It is very important for an EE student to look at the time signal and be able to interpret without any math what kind of Fourier transform it should have, right? That intuition is very important, okay? Of course, we are doing the underlying math here to some level of accuracy, but the intuition is absolutely something you need to get. All right, so that basically is an analog to, here's my notes, to the time domain property. So we have something sort of similar to that, with some differences. We no longer have this 1 over a coefficient, which is fine because we are in a different domain. We are not in continuous, we're in discrete domain. All right? Okay, any questions before I move on to another property? Yes? Then what happens is, okay, if I stretch it by a huge number, then I'm not going to see anything. I'm going to see a spike at 0, right? The value of the original signal at 0. And the value of the original signal at 1, I'm not going to see that guy for a long time, right? So you would expect then that the Fourier transform is going to look like the Fourier transform of a spike. Does that make sense? Is that consistent with what we see? Because if I'm stretching too much, then I'm compressing it, right? Oh, because of the periodicity, everything gets put together. So if you imagine this signal, actually this is a good question. I like this question. So look at this, right? So imagine taking m to be 1,000, right? So 1,000 of these peaks are going to be packed. So the one at 2 pi will now appear at 2 pi by 1,000. So those guys will be jam-packed together, right? So in the limit, that almost looks like a constant, the DTFT, which is the DTFT of an impulse, right? It's a constant. So that's because it almost looks like an impulse. The next value comes 1,000 steps later. Make sense? All right. Okay. So in continuous time, we talked about the derivative properties. And we got those by simply taking the derivatives of the analysis or the synthesis equation with respect to frequency or time, respectively, right? So now what we can do is something very similar. I can remember the analysis equation which said the DTFT comes from this summation, omega n, and then take the derivative of both sides of this equation by omega and see what happens. So d by d omega of this is going to be d by d omega of this, right? Okay. So, but d by d omega, I can put it inside the summation. So that basically makes the right-hand side equal to sum over n, x of n, d by d omega, e to the negative j omega n. And what is that equal to? That is equal to a factor times the original thing, right? What is the factor? Whatever is in the power that is not omega, right? And that would be negative jn, is that right? Okay. So that means the signal that is negative jn x of n would give me the DTFT d by d omega of x of e to the j omega, right? All right, so if you don't like this negative j on the left-hand side, multiply both sides by j. Okay, so then you'll get negative j squared equal to 1. So then this property will tell you n times x of n is going to give you a DTFT that is j times d by d omega of x e to the j omega. All right? So very similar to the time domain property. In time domain we had t, not time domain, in continuous time Fourier transforms, we had t times x of t giving us j d by d omega of x j omega. Same thing. All right? In CTFT, continuous time Fourier transform, we also took derivatives of the synthesis equation with respect to t, right? So we had an analogous result that said dx dt of t is going to give us j omega x j omega, right? There is no such thing in discrete time. Of course, there's no derivative, right? Because we're in discrete time, so there's no d by dt, right? The thing that would come closest to that would be to look at the differences, like the next value of x and the current value of x. Look at the differences, right? So, I just discovered something. I actually didn't need this pointer after all. I could use this. Okay. All right. So, okay. So, So the thing that is closest to that in discrete time would be to look at the difference x of n x minus xn minus 1, right? And that doesn't require any special results, any special properties. That already follows from what we know. Linearity, which says that I can just look at the individual terms and take their DTFTs. And the time shift. So this is a little pop quiz for you on the spot. So what is the DTFT of this guy? Of this? E to the negative j omega x e to the j omega, right? So the general property was x of n minus n0 will give you e to the negative j omega n0 times x e to the negative e to the j omega, all right? So therefore, this becomes e to the negative j omega x e to the j omega. So you can combine them into 1 minus e to the negative j omega x. Okay, so nothing special. We just use properties that we had already talked about. So, but to have some kind of analog to the continuous time differentiation in time property here, now that I discovered this, I might as well play. So something analogous to this would be the difference property in discrete time. All right, so no need to spend any more time on this. And as always, Parseval comes last. So it's always there. Nobody knows why. Well, but it shows up. No, I told you though, it gives you a nice geometric interpretation of these transforms as change of bases. So that basically means whatever are bases that I look at it, it has the same magnitude, right? That over n is, okay, take a guess. Remember, the DTFT is a hybrid concept because in continuous time, you're looking at discrete time things, but in the time domain, you're looking at discrete things, and in the frequency domain, you're looking at a continuous function of omega, right? So you can't really have summations on both sides, nor can you have integrals on both sides like we had in CTFT, right? So what do you think the right-hand side would look like? So it should be an integral. That's the most important part of the answer, right? Of the DTFT squared d omega. And there's also a factor of 1 over 2 pi, all right? You know, there are variations to the definitions of these Fourier transforms. Sometimes people put a 1 over square root of 2 pi initially in the definition. So when you come to this final property of Parseval, that 2 pi is not there. Big deal. You know, it's not a, you know, we don't worry about it too much. All right. Okay. Any questions? Okay, here's an interesting property. It's called the multiplication property. We did see something like this in continuous time as well, but we'll see a slight difference, and that difference will be a consequence of the DTFT being periodic. And you'll see what is going on. So the multiplication property says that if I take x1, multiply it with x2, what happened in, yes? Oh, yes. Thank you for reminding me. Absolutely, yeah. So I'm going to put a script 2 pi here, subscript 2 pi. Yes, absolutely. Thanks. So the multiplication property says that, what did it say in continuous time? Tell me. We had multiplication in time domain corresponding to convolution in the frequency domain, just like we had convolution in time domain being multiplication in frequency domain, right? Except for a factor of 2 pi. So similar thing happens here. So you kind of expect a convolution of the two Fourier transforms, right? X1, capital X1 and capital X2. But now those capital X1 and capital X2 are periodic functions. All right? So just like we had this little correction here in the Parseval definition, the convolution operation will also run over a period of 2 pi. And the rest is the same thing. You keep one of the functions as is. Let's say x1 remains a function of e to the j omega, but I'm going to use a dummy, call it theta, right? And then x2 will be flipped with respect to theta and dragged by omega, e to the j omega minus theta, integrated over theta, which is our dummy variable, right? So the integration will erase theta. Once you do the integration, theta is gone. But of course, what you've done depends on the omega, so that's why the resulting integral is a function of omega, and that's the Fourier transform of the product. So this is called a periodic convolution. The reason is the signals we are taking the convolution of are periodic themselves with period 2 pi, and we are doing the integration over a period which is 2 pi. All right, so that's how it differs from the standard convolution we saw before. Okay, so we'll see an example of this in a second. And while I have to make a call here, I guess I will choose not to show you the proof. Actually, not to do the proof, I'll show you the proof. That's always easy, because that's where what the notes are for. Okay, so this is the multiplication property. So what's happening is that we are basically going backwards to justify this property. So so what we are doing is we are taking the right-hand side of 11 and applying the synthesis equation to it. Right? Synthesis equation involves 1 over 2 pi, and then integrate this whole thing over omega. Right? So then you have two integrals. One is over omega, the other is over theta. The never-failing, very reliable trick in this course that saves the day in every lecture, in every exam, everywhere, is if you see a double integral or double summation, change their order, somehow that leads to the result. Okay? That's a meta trick in this course, all right? So this 11, the right-hand side of 11 has integral over theta. So technically we have integral over theta first, then omega. But if I change the order and take out of the integral anything that doesn't depend on omega, which in this case is x1 of e to the j theta, what remains looks a lot like I hate this. Looks a lot like the definition of the synthesis equation for x2. There's one key difference. The synthesis equation didn't have this negative theta term, right? But if you remember the property from last time, the modulation property, if you have something like e to the j omega n or e to the j theta n multiplying your signal, that shifts the spectrum by theta. Okay? That's basically the property we use for amplitude modulation, and it came up in the last time for DTFT as well, and it's identical. So then we can associate this with not x2 of n, but e to the j theta n times x2 of n using the modulation property. Okay, and once you do that, what remains in the integral? Also you can take x2 of n out of the integral. It's doing nothing there, right? And what remains is the pure synthesis equation applied to x1 of e to the j omega. So that gives you x1 of n. So in the end, you get the product. Okay. The multiplication property was proven in much the same way in continuous time. That's why I didn't want to prove it again, but it's in the notes, as you can see. Okay. So here's an example. But before the example, actually, I moved here too prematurely. So let's first do an example of the synthesis equation that I'm going to use in the real example I want to come to. Okay? What is a signal? What is a discrete time signal whose dTft would give me this? And omega c is where it ends, negative omega c. We answered this question for CTFT, right? What was it? What was the answer? It was a sinc, right? And when omega c was equal to pi, it was perfectly sinc t with no scaling factors attached to it, right? Now, but you should now start screaming because I can't possibly have a DTFT that looks like this, right? What's wrong with this DTFT? It has to be periodic, okay? DTFT has to be periodic. So if it looks like this at 0, at 2 pi, you need to have a copy of that, right? So it needs to repeat itself. Okay? So we have to be careful with that. Okay, but the question remains, what is the signal that does this to us? Okay? So what I can do is the usual thing. I can apply the synthesis equation to that, 1 over 2 pi. I can integrate over a period of 2 pi, for example, from negative pi to pi of this, but that will be 0 from negative pi to negative omega c, and it will be again 0 from omega c to pi. So therefore, there is no reason to integrate from negative pi to pi. It's enough to integrate from negative omega c to omega c, and what you're integrating is 1 itself times e to the j omega n integrated over omega, right? So what is the answer? Why am I writing this here anyway? So this should go here, right? Okay, so let's simplify this. Look at n equal to 0 first. What do you see? What's the integral if n is equal to 0? Well, 2 omega c, right? Because you're integrating 1 divided by 2 pi, so it's omega c by pi. All right, if n is equal to 0. Why did I do n equal to 0 first? Because for n different than 0, I'm going to do a trick that requires n to be not 0. If it's different than 0, then I do the indefinite integral, e to the j omega n by jn. Is that right? Would that be the integral of this? Yeah, if I take the derivative with respect to omega, I get jn, cancels jn. It works, right? Okay. So, and then the limits of the integration are omega c, negative omega c. So that means I'm looking at e to the j omega cn minus e to the negative j omega cn divided by pi n jn. Okay, I organized it, rewrote the order of the terms in the denominator because now I can see this really is sine, right? No, this is 2, what am I doing? 2j, right? 2j, and therefore I have sine omega cn by pi n, yes? And that is valid for n different than 0. That's why I took care of n equal to 0 first, because I have division by 0, all right? But the nice thing about the sinc definition is it takes care of this this discontinuity or the undefined term at 0. So the function sinc, remember, was defined as sinc of n would be sine pi n over pi n if n is different than 0, and 1 if n is 0, right? So if you don't want to write these braces every time, brackets, sine pi n over pi n, etc., make an exception for n equal to 0, we can use sinc. So let's write this whole thing as a sinc. How do you write this as a sinc? Any ideas? If omega c was pi, it would be great, right? It would be a perfect sink there. But it looks like it needs a little more work than that. So what if I say sink omega c by pi n? Does that work? It almost works, but it will introduce a coefficient, because sink of that, let me just write it here, sink omega c pi by pi n, by definition of sink, is equal to sine pi times this, that is omega c n, by omega c n, right? When n is different than 0. Is that right? Pi times, yeah, correct. Okay. And 1 if n equal to 0. Okay. So in terms of that, is that an accurate statement here? Something is funny here. Don't I need an omega c? I should have a factor of omega c by pi, right? Yeah. By n. Okay, because this is omega c, not pi, right? So this factor is needed to turn this into, to do the necessary cancellation. Okay, but to make a long story short, this term here is really equal to omega c by pi sink omega c by pi. All right, this is not a bad thing to write down somewhere and remember. Maybe a cheat sheet or something. I'm not saying I'll ask this, but it's a good thing, right? It's good to remember that. Okay, and what happens if omega c is pi? What does that thing on the left-hand side look like? It's just sink of n, right? Where is my n? And there's an n here, okay? All right, so if omega c is pi, then we simply have sink of n. And what does that look like? Sink is this function, right? And the way it's defined, it crosses 0 every time at an integer other than 0, right? But sink of n is an integer already. So we're talking about a discrete time signal. So the values of that at n equal to 1, 2, 3, 4, they're all 0, right? So yeah, you can call it sink of n. It looks fancy that way, but it really is an impulse, right? And what is the DTFT of an impulse? 1, straight. Why should this be straight? Well, because it's periodic. You see the ghost on the side, right? The orange one. So when you stretch omega c to pi, those two come together, right? And then it becomes flat equal to 1. Okay, so this is consistent with things we've already seen, all right? So take a mental picture of the thing at the top, all right? And I will give you an example, and then we'll take a short break, of how we can apply the multiplication property. So the example says that x of n is the product of two things. 3 over 4 sink 3 over 4 n, and the factors are given nicely so you don't have to worry about them, times 1 over 2 sink 1 over 2 n. Okay? So I can think of this as signal 1, x1 of n, and I can think of this as x2 of n. All right? So then I can use the multiplication property. So I will have, I will have to take the convolution of their DTFTs. But what are their DTFTs from our previous example? What is x1? It's a pulse, right? Where does it end? See, it was, if it's sinc omega c by pi n, then it ends at omega c, right? So 3/4 here is really, comparing to the previous result, 3/4 is basically omega c by pi, right? So that means omega c is 3/4 of a pi. So if this is pi, you're going to occupy this much of it. So 3 pi by 4, negative 3 by 5, 3 by pi by 4, and that is x1 of e to the j omega, right? And for x2, you have the same thing. What is the cutoff frequency now? Pi/2. Okay, so that's x2 of e to the j omega. And of course, these guys repeat themselves. All right? So we'll have to take the convolution of these two guys. All right? This is not your good old convolution. This is a periodic convolution. So to point out the differences, I'm going to go back to the notes and show you how that's done. Okay, so this is what we have to do. Look at equation 12. This is the periodic convolution that we just defined. And below you'll see how it works. All right? What 12 says is no different, really. It just says flip and drag the second one. The second one is the one that had omega c equal to pi/2. So it's a narrower box, right? The orange box is narrower. So let's choose to let x1 stay put, and we flip and drag x2. All right? And then we do the usual thing. We drag it, look at the, multiply them, find the area underneath. But because this is periodic, area means pick a period of 2 pi and evaluate the area over that interval. Okay? In this example, we will just do it from negative pi to pi. All right? So here's what happens. So the picture that you see at the top is second. The top is two of them superimposed as functions of omega. The second plot at the top is where you start seeing the convolution. That's for omega equal to 0. Because we flipped, nothing changed because it was already symmetric. And we didn't drag because omega is 0, right? So when you multiply them, you just get the shaded box. The rest is killed by the zeros of the orange function. And the area underneath is pi. Okay? Now you can start looking at omegas different than 0. That means dragging the orange box a little bit, right? But you see there's a little bit of wiggle room, right? Before the two touch each other. What is the space between them? Pi/4, right? So as long as omega is less than pi/4, that area is not going to change because, it's still an area of pi. Because the orange box is fully under the blue box, right? The moment you start exceeding pi/4, it is going to start sliding out. So you do expect to see the result of the convolution going down with omega. All right? So let me zoom in a little bit so you can see everything. Okay? So up to omega equal to pi/4, you have the integration constant. After pi/4, you start decreasing linearly, right? This is very similar to what would happen if you were doing the usual convolution of two boxes, right? In fact, we did take the convolution of a box with itself, right? It was the same thing. So since there was no wiggle room in that case, it became a triangular thing, right? The moment you drag, you lose a little bit of the area, right? But if one of the boxes were smaller than the other, narrower than the other, then there would have been some wiggle room, and it would have stayed constant for a while and then start decreasing, right? But then eventually it would have decreased and hit 0, because as I drag further, these guys will start splitting, and eventually they are split. At that point, you hit 0 and you stay 0, right? So you see this usual convolution, right? The difference here is this is periodic convolution. The two boxes can separate from each other, but the other box, on the periodic version of that box, the copy of that will start entering, right? So that's what I want to point out with this picture, the difference between the standard convolution and the periodic convolution. So after pi over 2, after a drag of pi over 2, whatever you're losing from the right, as the yellow box, the orange box moves out, is being compensated for by the copy of the orange box entering from the left. So that's why after a period of drop, the convolution stays constant. You lose area from one side, you gain it from the other side. They cancel out, so it remains the same. And that's a good thing, because whatever you get at the end will also be a periodic function of omega. Whereas this thing here, the usual convolution would give us something that is not periodic. Okay? So take a look at this picture. Make sure you fully absorb the difference between the periodic convolution and the standard convolution. All right, let's take a 5-minute break and continue after. How is the homework coming? Are you done? That means easy. Yes? Easy homework? It's okay. All right. Yeah, so I think there's no homework for next week because there's a big homework next week, which is the midterm, right? There will be instructions coming in the weekend from Dominic. And no reason to panic. Cheat sheets, okay. 1 page, letter size. 2-sided is okay too. You can use both sides. Yeah, I think the benefit of cheat sheets is more than actually, more psychological. It's there, you could use it. And also preparing it is instructive. So after next week, I think we'll assign another lab, a Python lab again. So I think you like those, don't you? Yeah. Okay. Anyway, so back to this figure. What's happening in the figure clear? So I show 5 samples of the result of the convolution, and each one corresponds to one of the figures. Omega 0 means you didn't drag this figure, second from the top. Omega pi over 4 means you dragged by pi over 4. Pi over 2 means you drag this much, right? So each of the red dots at the very bottom correspond to one of the bottom 5 figures. Okay, so it's in the notes. Obviously, when I made this, it took some time to prepare it. So make sure you look at it and follow it. Okay, so next thing we're going to discuss is the convolution property of DTFT, which is very similar, so we're not going to do any proofs. Why am I blanking out? Where's my... Oh, here. Okay. So the convolution property says the following. It says exactly what it said in CTFT. No difference, so you don't have to worry about anything. There is no accommodations to be made for periodicity and so on. It just comes as a result of the convolution property. It says that if I look at the convolution of x1, x2, and it will give me x1 DTFT of x1 times the DTFT of x2. If there is there are 2 sources of differences between CTFT and DTFT. One of them has to do with the discrete timeness of the signal, but in this case, that's not a problem. And sometimes differences arise because the DTFT is periodic with 2 pi, whereas the CTFT is not. But here there's no difference because periodicity follows directly, right? If x1 and x2 individually are periodic, their product is also periodic, so it follows automatically. So the proof is identical, almost identical to CTFT, so I'm not going to repeat it. But this is a popular property because it saves you from doing the convolution. Instead, you have to do a DTFT. So here's an example. And usually in the examples, the DTFTs will be some simpler DTFTs that we've already done as examples. So that will take no extra amount of work to do. So we'll just remember the DTFT from last time. So let's say x1 of n is some number alpha to the power n times the unit step. And for the DTFT of this to converge, the coefficient alpha has to be smaller than 1 in magnitude. And let's say x2 of n is beta to the n times u of n. And again, beta is less than 1. And we're interested in finding the convolution of the 2 of n. And I'll make your life easier and assume that alpha and beta are distinct. Okay? This will just help us in the derivation, but of course you can get around it if they are the same, and we'll do that as a separate example. Okay, so all I have to do is to remember that this has a DTFT that's the product of the 2 DTFTs. The first DTFT is what? You should remember this from last time. What's the DTFT of this? 1 over 1. Yeah, I should have called it A and B. I don't know. It's alpha, beta. But anyway, I started already. J omega, right? And for x2, we have the same thing, except that alpha is now beta, e to the negative j omega. All right? So this doesn't look particularly pretty, but if I can do what I called partial fraction expansion a week ago, that is, if I can write this as a number to be determined divided by the first term plus another number divided by the second term, then I've broken apart the product into two simple sums, and I know where each term in the sum comes from in the time domain, right? So if I can do this, assume for now that you can do that, right? Then, so if there exists a b such that, so this sign here is me being lazy and not writing there exists. Okay, so this sign is sometimes used to mean there exists, right? Just like for all, which is that sign, okay? Anyway, if I can find a and b so that this product can be written as such, then I've already found the answer, right? x1 convolution of x2 of n is going to be a alpha to the n times u of n plus b beta to the n times u of n, right? So that's the benefit of this property, because things are simple. If you know fundamental DTFT pairs, then you can use this to your advantage and not have to deal with convolutions. So the question is, what are the capital A and capital B? You don't know that yet. I said if. Oh, because then each one looks like the, if you forget about the capital A in the first term here, it's the DTFT of alpha to the NUN. Just like you told me that this x1 goes with this, right? Alpha NUN. So going backwards, this just scales it by capital A. So now, do they really exist, A and B? Turns out they do, because what you can do is you can try to match the two expressions here. This you can write as A 1 minus beta e to the negative j omega plus B 1 minus alpha e to the negative j omega. And you have the product of the two terms in the denominator. So to match them, so they match if A plus B is 1, because A plus B is what remains if I ignore e to the negative j omega terms here, right? That should be 1. And then the terms containing e to the negative j omega in the numerator here is A times beta plus B times alpha. And they should add up to 0, because I don't see any e to the negative j omega terms in this numerator, right? So under these two equations, the two terms will match, so our partial fraction expansion will work. Okay, so you're solving for two unknowns from two equations. How do you prefer to do this? Do you write matrices and invert them, or what's your preferred approach? Substitution, okay. All right, let's do it that way. Okay, so let's solve for B from this. So B is going to be negative A beta over alpha, correct? Is that right? Okay, then A plus B is 1 minus beta by alpha A, and I want this to be 1, right? So that means A is alpha over alpha minus beta. B is 1 minus that, which is negative beta by alpha minus beta. Okay? So you can now take this, substitute here, take that, substitute here, and you're done. There is a property that we needed here, right? Of course, these expressions for A and B don't make any sense if alpha and beta are the same. That's why I made that assumption. I said this is going to make your life easier. So it turns out that if alpha and beta are the same, then you can't solve for A and B. The two equations and two unknowns are not going to have a solution. So that means basically partial fraction expansion fails, which kind of makes sense because you have, if alpha and beta are the same things, you have this term squared, right? How can I write something squared as that term plus the same term, right? It just can't work. Okay, so that derivation relies on alpha and beta being different from each other. What do we do if they are the same? I'm asking you because I've done this once for continuous time. We use the convolution property of continuous time Fourier transform to deal with a similar example. There we call them A and B. We had e to the negative AT, e to the negative BT, right? And if they were the same, we couldn't use the partial fraction expansion. I guess I'm talking about last Thursday's lecture. That would be lecture 7. Do you remember what we did if alpha and beta are the same? We use the derivative property, right? So, which we already discussed earlier in this lecture. If alpha and beta are the same, we are looking at a Fourier transform that looks like 1 over 1 minus alpha e to the negative j omega squared, because alpha and beta are the same, so you take the square, right? Well, I can no longer do a partial fraction expansion to this, but I can try to write this as d by d omega of something and hope that whatever that something is the Fourier transform of something I already know, so I can go backwards easily, right? So what can you say about that now? Well, I mean, ideally it should look like this, right? Because that's the term that we know, right? So if I take the, let me first try to go backwards. So if I take the derivative of this, what do I get? I'll get some junk, right? In addition to this square term. And that junk we'll have to take care of by adding factors in front of this. Okay? So what is that? No, well, the the core first. What is? First, I'm going to get a negative 1. So this is d by d omega of 1 minus alpha e to the negative j omega inverse, right? So that you're going to get 1 over that squared, okay, which already is looking like what we want here, right? But then, what rule am I using? I always mix up the chain. Is it the chain? No, not the chain. Is it chain? Yeah, okay. Yeah, it's a composition of two functions, right? Now I have to take the derivative of 1 minus alpha e to the negative j omega with respect to omega, right? So I still need d by d omega of 1 minus alpha e to the negative j omega, right? And 1 doesn't do anything. I get negative alpha d by d omega of e to the negative j omega. And that just contributes, I guess, a factor of negative j, right? All right, so if you put everything together, every time we have to get a new factor, so their multiplication is going to be negative j alpha, I guess, right? Oh, I forgot the square. Alpha e to the negative j omega. And then there's, of course, this guy hiding here, e to the negative j omega. All right, so we have a lot of junk, it turns out, this squared. So what I call junk were these guys, all right? So I need to account for them. So what should go here? I should divide by negative j alpha to cancel this. And to cancel e to the negative j omega, I should multiply with e to the j omega. Agree? Sort of? Okay? All right. So, okay. All right. Now, what is the signal that gives me this Fourier transform? The derivative property that we discussed several... it's here. Wait, I went too far. It's here, right? Yeah, it's this one. Right? So this guy says j times that will come from n times x of n. X being, of course, the basic signal that is alpha to the n u of n. Right? U of n. That multiplied by n will give me j times that. Okay? So, okay, so if I that gives me j times that. So was it negative j here? Was that the property? It's that, but I'm not sure about the negative. That's why I'm looking back at my notes. Where is it? Okay. Yeah, negative j and x of n gives us that. All right, so that was right. Good. All right, so this comes with that. But then there are the junk terms that we have, right? So the first junk term is easy to deal with, this one. That's just a coefficient, right? So if I divide jn alpha n un by that coefficient, then I know I'm going to recover 1 over negative j alpha d by d omega of that thing, right? So j's cancel happily. So everything looks good. And in fact, there is a division by alpha, so I can even write this as n times alpha of n minus 1, right, times u of n, okay? So I took care of almost everything except that what I'm really interested in is not this. I'm missing this term, right? How do I account for this, right? I found a pair, which is perfectly fine, but really the Fourier transform I have is not this. It's that times an e to the j omega. How do I account for that? Time shift. Remember time shift property? I'm going to put it in a corner here. Time shift property said x of n minus n naught will give me e to the negative j omega and naught x of e to the j omega, right? So if you want to see an e to the j omega on the right-hand side, you should take your n0 to be negative 1. So x of n plus 1 would give me e to the j omega times x e to the j omega, right? So I can use this time shift property here. And so that means what I already have here times e to the j omega would come from this signal, except that it has to be shifted to the left. So it's going to be n plus 1, alpha of power n. It was n minus 1. Now I added 1. It became n. And u of n plus 1. Okay? Any complaints? Now, if you look at this a little closely, I mean, this is a perfectly fine answer. Nothing wrong with it. We found the answer. The lower left corner is the answer to the question. The convolution of alpha to the n with itself looks like this. Okay? N times alpha to the n. This is very similar to our continuous time example when we had e to the negative at convolution with e to the negative at, one-sided signals, of course, was t times e to the negative at, right? And now I have n plus 1 times alpha to the n. So it's kind of similar. So where does the signal u of n plus 1 start? What is the first time when u of n plus 1 is not 0? And negative 1. So according to what I wrote, this signal could start as early as n equal to negative 1. But what factor does it have when n is equal to negative 1? What happens to n plus 1? 0. So really there is no different than saying n plus 1 alpha to the n u of n, because nothing happens when n is equal to negative 1. It's still 0, right? So nothing is lost if I rewrite it that way. And with that in mind, it looks very similar to the t times e to the negative at term. All right, so that's how you get around your the case alpha equal to b. You just use the derivative property. All right. So u of n plus 1 itself is already non-zero at n equal to negative 1. But remember that is being multiplied by n plus 1. And at n equal to negative 1, n plus 1 is 0. So even though u of m, so you're multiplying two signals, n plus 1 alpha to the n, which at n negative 1 is equal to 0, right? And it does other things, right? And then u of n starts at negative 1. But when you multiply them, this 0 kills it, so you might as well ignore this. Okay? All right. Okay, so that's a good enough illustration, I guess, of this. Time shift and convolution properties. All right. Here's a little, I'll go to the notes. Here is something that puts everything together. A cute example where we get to practice everything we learned so far. Just take a moment to look at this question. So this is an example that trains almost all of your, properties. You have to use all of them. Almost all of them. Quite a few of them, at least. Okay? So you have designed a low-pass filter. Okay? So perhaps the ideal low-pass filter that is 1 up to omega c and 0 after. Right? And I don't even know why I said... Oh, omega c less than pi over 2. Okay, fine. I didn't say omega c pi over 2. It's anything less than pi over 2. Anyway, so we do know what HLP to the j omega looks like. It looks like this. Omega c, 1, and at 2 pi you get another copy of that. Right? All right? So let's do some work here. So let me now think of the Fourier transforms, DTFTs of these guys here, of all these signals that are marked, W1, right? So this is x of n. This is x of n, right? So W1 of n is negative 1 to the n x of n. So what would be W1 DTFT in terms of the DTFT of x? This is a modulation property candidate in disguise because we saw this last time. Negative 1 to the n. Negative 1 is e to the j pi, right? So I can write negative 1 to the n as e to the j pi n. And the modulation property tells me that pi being my frequency, I should just shift the spectrum of x by pi. Okay? So then the answer is x e to the j omega minus pi. Okay? That's all that happened. All right. So let's write down the property we use every time. So bi-modulation property. And we discussed that in the last lecture. Okay. Now I'd like to know W2 e to the j omega, W2 being this signal. So what is W2? What stands between W2 and W1? A low-pass filter, but it's in time domain, it really is convolution with the impulse response of that filter, right? You don't want the convolution here. We're talking about DTFTs. We're talking about Fourier transforms. So convolution in time domain becomes multiplication in the frequency domain. So therefore, W2, the DTFT of W2 is the frequency response of the low-pass filter times x. Well, okay, let's be clear. Okay, times W1 e to the j omega by the convolution property, and W1 I know is equal to this term. So you take this, substitute it here, so you get HLP e to the j omega times x e to the j omega minus pi. Okay. Now, what is W3? Which is here. W3 of n again is negative 1 to the n times W2 of n. So that basically shifts the spectrum of W2 by pi. So you're going to get HLP e to the j omega minus pi. And then do the same thing to x. What do you get when you do the same thing to x? You recover x, right? Because it's periodic. Omega minus 2 pi is the same as omega, right? E to the j omega. Okay? So the nice thing about this notation, which I know is a little annoying, why don't I write x of omega, but I write x of e to the j omega? It's immediately clear that it's periodic with 2 pi, right? Because omega doesn't appear alone in this expression or in the definition of DTFT. It always appears as the factor of, as the power of E multiplied by j, right? And because of that, if I add 2 pi to omega, I still have e to the j omega. So it kind of reminds you of this periodicity, which in this case was useful. All right, so we recovered x itself. Only it got multiplied by a shifted version of the low-pass filter. So what happens if I take the low-pass filter response that was centered at 0 and shift it by pi? What kind of a filter do you get? This moves to pi now. Pi is the high frequency. Now it becomes a filter that passes high frequencies, gets rid of low frequencies, right? So if I'm just interested in how W3 compares to X, it really is a high-pass filtered version of that. But I'm asking more than that. I'm asking what is Y? How is Y related to X? What is Y? Y is W3 plus W4. So Y of e to the j omega is the sum of the two. Essentially, the quick answer is I'm adding a low-pass filtered signal to a high-pass filtered signal. So I passed low frequencies, I passed high frequencies. If there was a little gap between those two, whatever frequency lied on that gap, that got stopped. Okay? So this would be a band stop filter. That's a quick answer, but the purpose of this example was more to practice the properties. Here I use linearity. And I know W4 is HLP e to the j omega times x e to the j omega. Okay? So put them together. wait, what am I? Yeah, okay, W4 is this. And therefore y, which is the sum of them, is HLP. I'm going to drop the arguments because I'm running out of space. Plus HP, I'm going to say that's this one, HP, times X. All right? So if I look at the next slide, all of this is done. And the sum of the low pass and the high pass are going to give you a band stop filter. It will stop anything between these two corners. The reason I assumed omega c was less than pi over 2 was to actually leave a gap there, right? And that gap is what gets stopped, right? If omega c becomes pi over 2, no gap is there, so it's not band stop. All right? Good? All right. In the remaining little amount of time, let's talk about discrete time difference equations. So a good source of LTI systems, remember, are given by differential equations in continuous time, linear constant coefficient, and in discrete time they come from difference equations. So the general form of a difference equation we've been discussing was like this. K0 to n. You might have delays going up to capital N, and that is equal to K0 to M B sub K U, not U, X, right? X is the input. X of n minus K, right? So this is our difference equation. Linear, constant coefficient, AK and BK don't depend on time. Okay, so I want to find the frequency response of this signal. Just like we observed in continuous time, frequency response is really, the way we defined it in the third lecture, is the same as the DTFT of the impulse response, right? So we call frequency response. I didn't do this explicitly for DTFT, but I did it for CTFT, and it's the same thing. Is Fourier transform of impulse response, and the same thing is true for a discrete time system signal, and so DTFT comes into play. Impulse response, okay? So in principle, I could work on these difference equations, pick up some old books that tell us how to, remind us how to solve difference equations, and for the input select the unit impulse, delta, right? For X select delta. So what that does is it kind of gives you an initial condition, because for this to be an LTI system, it has to start at rest, right? And so using the delta, I can increment one of the initial conditions and solve this. It essentially becomes almost like a homogeneous difference equation. Anyway, so you can technically go through a lot of algebra and find the impulse response, okay? But now that we know about Fourier transforms and we know this key connection between the frequency response and the Fourier transform and the impulse response, we don't need to do that, right? I can actually recover the impulse response from the frequency response of the system. And how do I find the frequency response? That's actually fairly easy. To find the frequency response, substitute for X the impulse, and what that gives me is the impulse response, AK H n minus K is sum BK delta of n minus K, all right? And then take DTFT of both sides. Okay? So forget about the summation for now. What is the DTFT of this? in terms of the dtft of h. What property do I need? Time shift. So I'm going to get e to the negative j omega times k times the dtft of h, which is my frequency response, right? And then how do I account for ak? Just put it here. What property did I use? The scaling, linearity, right? And because of linearity, again, sum also goes here as well. Okay? Same thing happens on the right. I get sum bk, and then e to the negative j omega k times the Fourier transform of a delta, which is 1. Therefore, I don't need to write anything there, right? And so when you look at the left-hand side, you're doing a summation, and everything in the sum has a factor of h. So I can pull h out of that sum, right? So that means h of e to the j omega, very conveniently, is sum bk e to the negative j omega k and sum ak e to the negative j omega k. And we have to be careful, of course, with the summations. Here it goes from 0 to n. Here it goes from 0 to n. Okay? All right. That's nice. So we have a... Now we know how to go from a difference equation to its frequency response directly, right? I don't need to even remember that there is a impulse response in the middle connecting them. You just look at the coefficients of your difference equation, you plug them in to this expression here, and that you get the frequency response. Isn't that convenient? So the impulse response was used as a stepping stone in the derivation. I don't need to know what it is, right? In the end, the frequency response is given by that. In fact, if I want to know explicitly what the impulse response of this system is, probably the easiest thing will be to take this frequency response and take its inverse Fourier transform, that is, apply the synthesis equation to it, or use partial fraction expansion or whatever have you, to go back in a simple way. All right? So here's an example that illustrates this. I'm going to give you, so take a mental picture of this at the bottom. And don't even memorize this, because, you know, if you look at this derivation, it's very simple to see how these terms appear in the numerator and the denominator, right? So this is something you can do in 2 seconds. It's not worth the space in your cheat sheet. Okay. Well, it's up to you. I can't tell you what to put in your cheat sheet, okay? So here's an example. So here is a difference equation. 1 over 8 y n minus 2 equals 2x of n. Okay, and tell me right away, what is the frequency response? Okay, what goes in the numerator, what goes in the denominator? Two goes to the top, right? All right. So maybe instead of memorizing a formula that was on the previous page, the thing to remember is things on the right-hand side are going to go to the numerator, right? And things on the left-hand side, things on the y side, the output side, right, they will go in the denominator. And y itself will just give a constant, and y is multiplied with 1, so you just put a 1 corresponding to the coefficient of y. For y of n minus 1, I have a coefficient of 3 over 4. And because that's a delay, right, it contributes e to the negative j omega, right? And then 1 over 8 comes here, multiplied by e to the negative 2 j omega, because that's delay by 2, right? So it's good to see this pattern instead of looking at a dry formula like this we had here. So just in your mind, make the connection between how the coefficients go in the numerator and denominator. Where do they go? And that's all there is to it. Okay? All right. So, okay. Okay. So now the question is, how do I go back to the time domain so I can find the impulse response? So you already done, I didn't ask you what the problem is. The problem is part A, find the frequency response, done. Part B, find the impulse response. Let's do it. How do I do it? I just have to go back to the time domain from here, right? Does that look pretty, the Fourier transform I'm looking at? Well, it has e to the negative j omega. That alone would be okay, but then I also have 2 times that. I mean, it's power of that, second power of that. So the best bet would be to factor this out as 2 stays where it is. But if we could factor this out in this form, then this is a great candidate for applying the example we already discussed, right? When we had a product like this, we used the partial fraction expansion and went backwards. It was very easy, right? So do you think we can find alpha and beta like that? So imagine multiplying these two in the denominator, right? So then I will get the product of alpha and beta. That would have to match 1 over 8. And I would have the sum of alpha and beta. That would have to match 3 over 4, right? Alpha, beta is 1 over 8. Alpha plus beta is 3 over 4. And I think you had an answer to that. So alpha is 1/2 and beta is 1/4. What are you saying? No, because these have negative signs too. Obviously, it doesn't matter which one is 1/2, which one is 1 over 4, right? For the same reason that, you have a product here. Which one you call alpha is your call, right? So let's say alpha is 1/2 and beta is 1 over 4. So then what we want to do is we want to write this guy as, so we determined this is equal to 2 over 1 minus 1/2 e to the negative j omega times 1 minus 1 over 4 e to the negative j omega, right? So our trick is to write this as a number A by 1 over 1 minus 1 over 1 minus 1 over 2 e to the negative j omega plus B times that, okay? Okay, you're saying good things. That saves me time. You're saying A plus B is what? Y. 2, right? And what else did you say? Is 0 because there is nothing like that, no e to the j omega term here, right? Okay, so B is negative 2A. This means B is negative 2A. And put it in here. That says negative A is 2. So A is negative 2, B is 4, I guess. Is that right? Yeah, you're right. So what, wait, but I just did what you told me. Okay, so. Oh, okay. That makes sense. Okay, B over 2. So A is negative 2B. A is negative 2B. Therefore, negative B is 2. A is 4. No, I don't know what's going on. Just tell me the answer. This is not worth our time. So what are you saying? A is what? B is what? I won't question you. A is 4? Okay, good. All right, so that means using this, we really found the answer. So we found the Fourier transform of y. I'm sorry, the Fourier transform of h to be 4 times this and negative 2 e to negative j omega, right? So therefore, I know where this comes from. This comes from 4 times 1/2 over power n. And this comes from 2 times 1 over 4 to the n. And they are both one-sided signals, so they get multiplied by u of n, right? So here's a modern or enlightened way of, finding the impulse response. Rather than hassling with the difference equation, you just do algebraic manipulations of the Fourier transforms, and you find the answer. And same goes actually for solving this difference equation, right? If I gave you an x, ask you to solve it, as long as you're starting with 0 from rest, and x is a right-sided signal, you can just use the same ideas and solve for y. Okay, there's one more question in the notes. Very simple. Look at it, and that's it. Okay? So I'm going to see you next time.